Hi, I'm Don Patterson.
And I'm Bill Tomlinson, and this is our paper, Proof by Location as a Socially Responsible Financial Infrastructure. So we'd like to start off by talking about what are some of the problems with existing cryptocurrencies. So first off, cryptocurrencies often use large amounts of energy. So for example, Bitcoin uses 707 kilowatt hours per transaction, a number that has been critiqued in both academic and news sources. Ethereum uses 64.2 kilowatt hours per transaction as well. So the use of large amounts of energy is a real problem for cryptocurrencies and potentially limits their ability to become a dominant financial infrastructure because of the social challenges that come along with that energy usage and the CO2 that they produce. A second issue that is perhaps less noteworthy at present, but nevertheless is similarly significant from a social perspective, is that cryptocurrencies tend to contribute to wealth inequality. So there's an index called the Gini index that describes how unequal the incomes and wealth of a certain population is. And with the mean of all countries around the world, the mean Gini index is around 37.6, which is partway between 0, meaning perfect wealth equality, and 100, meaning that one individual has all of the wealth. Bitcoin, however, has a Gini index of 88. So the Bitcoin ecosystem has an Gini index of 88, and Ethereum has a Gini index between 76 and 91, depending on how you count. So significantly more wealth inequality than in other human contexts. So the use of the large amounts of energy is problematic because climate change leads to all sorts of challenges. For example, it leads to sea level rise, which is projected to cause 216 million climate migrants by the year 2050, according to the World Bank. And wealth inequality is also a significant social problem. It leads to increased food insecurity and lowered population health and increased ecological degradation. So these are all some really significant issues that cryptocurrencies in their current form contribute to.
So Bitcoin uses a lot of energy, and all of the digital financial transactions exacerbate inequality, financial inequality. So what have other people tried to try and alleviate some of these challenges? Well, Bitcoin uses proof of work, which is the problematic mechanism by which we achieve consensus in the transactions. Proof of work relies on a number of different computers competing in order to solve cryptographic puzzles. The fact that you've solved a cryptographic puzzle means that you've done a lot of work, a lot of computational work, resulting in a lot of wasted CPUs, a lot of wasted CPU cycles. An alternative to that is called proof of stake. Proof of stake is perhaps most well known as the mechanism that Ethereum 2 uses in order to achieve consensus. Proof of stake, sort of simplified a little bit, allows certain individuals that own a lot of cryptocurrency to consolidate, form a block, and then to sort of assert based on their cryptocurrency holdings that this is a valid financial transaction block. The risk is that if they lie or they attempt to do some sort of malfeasance associated with their assertion that this is a good block, through the mechanisms of the proof of stake algorithm, they risk losing their cryptocurrency. So the argument for why this is a good mechanism is because people who have a lot of currency are incentivized to make sure that the system is sound and continues to work. Another mechanism is proof of authority. Proof of authority is a fairly simple mechanism. It says that there are certain identities, certain people that are trusted in order to form blocks, in order to authorize transactions, and that these identities are known. And so when a block is closed, when transactions are authorized, it is a particular person who has authority in the blockchain to close the block. That's another mechanism. A fourth one is called proof of weight. Proof of weight is a consensus building algorithm that's very similar to proof of stake, although how much you use your holdings as in the cryptocurrency as a kind of weighted vote towards closing a block or a set of transactions. Delegated proof of stake is like proof of stake. It just is offered down to a smaller committee of cryptocurrency providers. And then finally, proof of burn is a mechanism of sealing a set of transactions in a block by throwing away currency and demonstrating that you have thrown away some currency, another attempted mechanism to achieve consensus. So there have been some other attempts at trying to find alternatives to the original Bitcoin proof of work algorithm. We looked for something that was similarly inviolable in the same way that you can't cheat a cryptographic algorithm. Proof of work requires you to do work in order to be able to solve a cryptographic protocol. Proof of stake argues that you must have a certain amount of cryptocurrency, and also through cryptographic protocols that can be validated by looking at the blockchain. Other mechanisms are possible, but we wanted a kind of inviolable principle that we could base a blockchain consensus mechanism on. And we arrived at the idea of using the speed of light. Because the speed of light cannot be broken, we can't go faster than the speed of light, we used that as a mechanism by which we validated that different participants in the blockchain validation process were located a sufficient distance away from one another. We did this by measuring the amount of time that it takes for packets to travel between nodes in our consensus building algorithm. And through the time that it takes for that to happen, we both assert that the block is valid, and we make sure that it takes that double spend attacks are not possible. We, for our method, what we did is we went through and we created a basic implementation of this algorithm in Java, and we ran a bunch of simulations of the protocol running with a lot of agents executing the algorithm, around the globe with simulated times between them, because obviously we don't have a lot of people using this algorithm yet. So that was our approach, and that was what we added. So what I'd like to do now is walk through the steps of our protocol, demonstrating at a high level how it works, and then in future slides we'll step through some of the details. So on this slide here, we have a proposed transaction, a transaction that begins with Anna and walks through 7 different steps of our protocol. Anna wishes to send our currency, Xylem, to another participant, Bob. So she initiates a transaction and sends it to a transaction maker, one of the computing nodes that exists in our network. The transaction maker accepts the transaction on behalf of Anna, validates that she has the currency that she claims to have, and validates any other properties that the transaction maker would like to validate, possibly requiring identity checks, possibly requiring other kinds of properties of the transaction. The transaction maker then holds the transaction until the recipient, Bob, agrees to accept the transaction. This recipient approval process is one of the ways our protocol differs from other protocols. For example, Bitcoin, in which you can send currency to any recipient regardless of their participation in the transaction. Once the transaction maker has received acceptance from Bob that the transaction is desired, the transaction maker passes the transaction on step 3 to the block checker. The block checker holds a transaction pool of transactions that have not yet been placed into a block and therefore have not been officially spent yet. As part of being in the transaction pool, the block checker in step 4 passes the transactions around to other peer block checkers in a gossip protocol so that all of those block checkers have transactions available to them for block making. In step 5, a block checker forms a block and sends the block to a third kind of node in our network called a notary. It's at step 5 where the proof by speed of light occurs. Passing the block around between the notaries and the block checker entails a certain amount of time dictated by the distances between the nodes. That distance is both a proof that the notaries are where they are, and it is a mechanism that prevents double spending because of the necessary delay in passing this packet around the globe. So after step 5 occurs, and a block checker has formed a block full of transactions from the transaction pool and had it validated by the notaries, in step 6, the block checker gossips the signed and proven block out to the blockchain, adding it onto the blockchain similar to other blockchain mechanisms. That block is picked up in step 7 by other keepers being a superset of transaction makers and block checkers, who are maintaining the validated blocks between them and keeping track of the blockchain in a way that's typical for other cryptocurrencies. This slide demonstrates the specific process by which a transaction is submitted into the approval pool. It consists of a series of signatures and hashes of a particular transaction so that everyone knows that Anna has initiated the transaction and Bob has approved the transaction. It begins by Anna submitting an encrypted transaction to the transaction maker. The encrypted transaction has a number of inputs that are known, basically solving the UTXO of a previous transaction, similar to the way that Bitcoin operates. And these inputs are known and are visible, so that the transaction maker can validate that they are in fact unspent transactions according to the current blockchain. The outputs, however, are encrypted, and they are encrypted against the public key of the recipient. For example, Bob 1, Bob 2, and Bob 3 in this diagram. Bob 1, Bob 2, and Bob 3 must be contacted through a URL, email, some kind of instant messaging, whatever the transaction maker supports, at which point Bob must respond by decrypting the transaction output and returning it back to the transaction maker. In addition to these encrypted outputs, there's also a transaction maker fee, a fee that goes to the transaction maker for doing this work, as well as a location proof fee that goes to future participants in the proof network. Once Bob 1, 2, and 3 has decrypted the outputs of the transaction, it's now possible to see that the outputs have been signed by Anna and therefore valid because the encryption encrypted the signed output. And so now the transaction maker has access to a transaction that includes inputs that have been validated and a number of outputs that have been decrypted and are able to be passed on to the transaction pool, which can now hold a complete and validated transaction approved by Anna and approved by Bob for inclusion into the blockchain mechanism, included into the block proof mechanism.
To notarize a block, each block checker takes the hashes from the previous blocks in the blockchain and converts them into a set of latitude and longitude locations at various target points around the Earth. The block checker who is closest to the first of these targets becomes the lead block checker and organizes the block notarization process. The lead block checker works with a subcommittee of other block checkers notaries, each of whom are the closest to one of the other geographic targets to notarize the block. The subcommittee block checkers perform speed of light location verification on each other and on the notaries that they're working with. They then exchange information about each other's response times. They then compare these response times with the reported locations for each of the block checkers and notaries that were stored on the blockchain previously, and use that information to calculate eigentrust values for each of the members of the subcommittee. The lead block checker then begins a notarization chain, including all trusted block checkers and notaries, that is, those with a high enough eigentrust score to demonstrate that they weren't lying about their position. This notarization chain goes from the lead block checker to each of the other block checkers in turn, who then sends it out to the subcommittee notaries who are nearest to them. Each block checker and notary signs the block before passing it along. Due to the distance between the various subcommittee members, the limitation of the speed of light in this process creates a delay that is analogous to the one created by the proof of work process underlying Bitcoin.
At various points in our block proof mechanism, it's necessary to randomly choose locations on the surface of the planet. So to do that, we use a geographic hash function. Our geographic hash function uses properties of the blockchain to produce random locations on the planet that are not knowable before the previous blocks have been solved. And so it's impossible to pre-compute these locations.
We've performed some initial evaluations on the system, and we have found some promising preliminary results. So first off, it's able to maintain a throughput that is on par with or above all of the other major systems we compared it to, including Bitcoin and Ethereum, both versions, as well as Visa, with the possibility of 125,000 transactions per second. Second, we found that it had a significantly lower energy usage per transaction, several orders of magnitude lower than Bitcoin and Ethereum W, significantly lower than Ethereum, and lower even than Visa per transaction. And you can see the charts here on the slide. In addition, we found that this proof by location system potentially reduces wealth inequality as well. So we created in a simple simulation that compared the system that we're building to Bitcoin, Ethereum, Ethereum W, and Visa, and found that the system that we're creating reduces wealth inequality, that it causes the Gini index to fall, whereas all of the other systems cause the Gini index to increase, which is on par with what we would expect given the information that has previously been studied about the wealth inequality. This paper has presented a novel mechanism for enabling a distributed global consensus to confirm the integrity of digital financial transactions. The associated platform, Xylem, is designed to have lower environmental impacts than existing financial infrastructures such as Bitcoin, Ethereum, Ethereum 2, and Visa. Notably, it is also designed to distribute transaction fees geographically to support broader participation. The tendency for existing proof-of-stake algorithms to support wealth centralization is a critical and underappreciated shortcoming of previous approaches that our system corrects.
Financial systems are an important part of the global socio-technical infrastructure, and any changes to them should be justified from both a social and a technical perspective. We therefore propose the Xylem architecture that we've described previously, platform and a cryptocurrency, as a step toward providing a better user experience, a better economic infrastructure, and a better social mechanism by which people engage in payments around the world.
We would like to thank the students we worked with on this project, Ethan Banez, Evelyn Chin, Hayden Friedman, Nicole Sullivan, and Ishan Varney for their contributions to the project, and also to Adrian Berthlow and the reviewers of this paper for their feedback on our work. Thank you very much.